This conference will now be recorded.
Hello everyone. We are starting a new chapter which is haloalkanes and haloarenes. So first we will see what is haloalkanes and what is haloarenes, and then there will be classification for these two types of compounds, and also after that we will see the rules for their nomenclature and some related problems. So the first question is, what are haloalkane? This is the first term. And what is haloarene? Now here, after halo, what is mentioned? It is mentioned alkanes, and after haloarene. Now when we say alkane, that means it is containing only carbon and hydrogen, and it is saturated compound. That means there is no CC double bond or triple. And when we are calling it arene, arene ring is basically maybe any derivative of phenyl. So if it is simply benzene ring, we write it as PH. But suppose there are some substituent present, there may be any substituent, so I am writing in general like this. So G is suppose the general substituent, it may be bromo, chloro, OH, NO2, whatever. So this is arene, that means it may be any phenyl ring containing derivative. Now when we are saying haloalkane, that means alkane which is carbon and hydrogen, containing only carbon and hydrogen, their hydrogen will be replaced by some halogen. So that is why the name is haloalkane. And in case of arene, here if hydrogen of the benzene ring is replaced by some halo group, then it will be haloarene. Now come to the definition. When one or more hydrogen atoms of aliphatic or aromatic hydrocarbon, okay, are replaced by the corresponding number of halogens. Now halogens means it may be fluoro, chloro, bromo or iodine. Now the resultant compound, they will be called, see, different terminologies are there. You can call it alkyl halide, which is basically the common name, we use it very frequently, but it is also known as haloalkane. And when it is attached to aromatic ring, now the name will be either allyl halide or haloarene. Fine. Now haloalkane, obviously they contain halogen atom, or in bracket it is mentioned S. That means it may be more than one halogen. Fine. And it is attached to sp3 hybridized carbon atom of an alkyl group. That means in general you can write the structure as Rx. Rx means suppose you have alkane. Alkane is RH, and this R group is basically containing carbon and hydrogen. So one of the H, if it is replaced by some halogen, now it will be transformed to Rx. So for example, you can write, suppose you have methane. So methane you can write in this way, CH3, and with carbon there is another hydrogen. So this is the R group. Now if this H you are replacing with some halogen, suppose if it is chloro, now it will be Cl, then CH3. So its name will be methyl chloride or chloromethane. Okay. So here one hydrogen in methane, which is having formula CH4. But now as one hydrogen is replaced by Cl, now it is CH3Cl. Okay. And in case of haloarenes, now it also contains halogen atom or atoms, but it is attached to sp2 hybridized carbon atom, because now we are talking about phenyl ring, and in phenyl ring all the 6 carbon atoms are sp2 hybridized. So that is why now we are replacing the sp2, the hydrogen which is attached to sp2 carbon, by halogen. And in general you can write it as ARX. Normally if it is simple benzene ring, you can directly write PHX, but suppose if in PH ring there is some other substituents, then better you use the term AR, which is short form of aryl. Fine. So as if benzene ring is there. So when simple benzene ring is there, we write it as, it is equivalent to PH H, because when it is pH, it is basically C6H5. Benzene ring is what? C6H6. But when we are saying phenyl ring, it is basically the substituent. That is just if you decrease one hydrogen, it will be C6H5, and that is attached to H. Now, if in this pH ring there are some other substituents. Suppose you have OH substitute. Then it is better you write it as ARH, not pH, because now it is not simple phenyl. And this H, that is any of these 4 hydrogen, if you are replacing with halogen, now it will be ARX. Fine. Now, if we compare their change in properties, when you are first having some alkane or you are having some simple aryl group, and now you are replacing one of the hydrogen with halo. So there will be some change in its physical properties and also some structural change. So there is fairly large distinction between the structural and physical properties of haloalkanes and alkanes. That means previously when you have only carbon hydrogen in the molecule, it is alkane, but now you have replaced one hydrogen with some halo group. It may be one halo or more than one, but even replacing one each with some halo, that is even if it is one halogen atom, then also there is a change in the physical property, and it has to be because you are changing H. It is due to replacement of one or more H with X. So H you are replacing with X. So obviously now the X compared to hydrogen, it is more electronegative in nature, and also there are some other differences. So it has direct effect on the structural property and also on the physical property. So these differences in physical properties, difference between what? Physical property of alkane and physical property of haloalkane. So these differences in physical properties, these are results of factors. That is, what are the reason for which there is difference in physical properties between haloalkanes and alkanes? The reasons are electronegativity, obviously, because halogens are highly electronegative. Remember in the periodic table they are on the right hand side, the group 17, right? And we know that as we move from left hand side to right hand side towards the periodic table, electronegativity increases. So they are the most electronegative. And fluorine, that is the first halogen in this group, that is the most electronegative element in the whole periodic table. So very large difference in electronegativity and then also in bond length. And why we are talking about it? Because first you have CH bond, but now you have CX bond. And even if you consider the smallest halogen, which is F, but still it is larger than H, right? So this bond length between carbon and H, this bond length, and now the new bonding between carbon and the halogen, obviously there will be some change. Then change in the bond strength, because now you are changing the element with some other halogen, so different elements, so bond strength will also be changed. And overall molecular size, that is overall if you consider the size of a single molecule before replacing the H with halogen, obviously there is also some change. Halogen substituted organic compounds, they are very common, they are widely spread in nature, so their natural occurrence is also very high. And in our day-to-day life there is also versatile application of it, so that is why they are very important. Okay, that is, there is a separate chapter we are discussing for these types of compounds, so it must be having some important application. So that is why it is important for us to know what are its distinct feature, that is compared to the haloalkane or compared to alkane, that is when you do not have any halogen and you have now inserted halogen instead of by replacing H. And in case of aromatic molecule, you have replaced one of the aromatic hydrogen with some halogen. So there are some differences. Classification. Now, when we are doing classification, first we have written here organic halogen compound. Now, normally if we say haloalkane, we consider it that there is no unsaturation, that is you do not have any CC double bond or CC triple bond. It is only carbon and hydrogen, there is only single bond, all the carbons are sp3 hybridized. But when we are saying organic halogen compound and we are doing this classification, in this case you will also see that even in haloalkane if there is some CC, there may be some CC double bond or CC triple bond present. Fine. Though when you say alkyl halide or haloalkane, there is no sp2 carbon or sp hybridized carbon. But when we are doing classification, we will see all the possibilities. Fine. Now this classification, it can be based on different things. The two main factors here, you can do this classification based on hybridization of the carbon with which the halogen is directly attached. So it is true that when it is haloalkane, the carbon is sp3 hybridized, that we have already seen in the previous slide. When it is haloarene, then the carbon is sp2. Okay, so all those things we will discuss under this heading. But first look at this left hand side. It is based on the number of halogens. So it is comparatively simpler. You can easily understand it based on number of halogens. That means if it is one halogen, then it will be monohalo compounds. For example, if you see C2H5Br, you have only one bromine. So this is monohalo. Or if it is more than one halogen, that is di, tri, tetra, then we can, in general, we can write it as poly. That is just more than one, it will be under poly. Now we will see some examples under this type of classification. Remember, this classification is based on how many number of halogen atoms are there. So this is the number one method by which you can do the classification. And the second one, that is based on the hybridization of the carbon with which the halogen is attached. So that we'll discuss later. First, look at this first classification, which is based on number of halogens. So when it is based on number of halogens, on the basis of number of hydrogen, they can, sorry, it is halogen. They can be divided into mono, dry, or poly compounds. It may be tri, tetra, and more than that. Compounds of haloalkane and haloarene. So here we have very simple mono haloalkane because you have only one halogen atom, C2H5X. So the corresponding alkane, if you write, it will be C2H6 because here it is 5 hydrogen, but when you are removing the X, you have to place H. So this is the corresponding, that is a mother compound from which you are making the halo derivative, which is C2H5X. So you have replaced one H of ethane, that is C2H6, by halogen atom. So that is why it is monohaloalkane. Now C2H6, same alkane, if you now replace two different halogens. Now C2H6, if I write in this way, CH3, CH3. And now if you are replacing one H by X and the second H from the second carbon by another X, now it is dihaloalkane. Look at this structure. Then in benzene ring, that is in case of haloarene, when you have only one halogen, it is monohaloarene, but you may also have dihalo. Here their positions are ortho position. At 1 and 2 position, it may be 1, 3 or 1, 4, that is meta and pan. But it is dihaloarene, whatever is the position, because number of halogen is 2. Then try CH2X, CHX, CH2X. So if I tell you to write the corresponding alkane, it will be CH3, CH2, CH3. So all these three carbons, the first carbon 3 hydrogen, second carbon 2 hydrogen, last one again 3 hydrogen. So from all these carbon, just replace one H from each by X and it will be trihaloalkane. Same thing if you do in some benzene ring, that is 3H of the benzene ring, now you have replaced by 3 halogen, so it will be trihaloarene. In this case, their positions are 1 to 3, but it may be 1 to 4 or it may be 1 to 5. So different positions may be there, but common thing is all of them are trihaloarene. Now the other classification, if we now elaborate it, based on hybridization of carbon with which the halogen is attached. Now this classification, further two possibilities are there. One is if compounds containing carbon sp3x, that means halogen is attached to sp2 hybridized carbon. That is one possibility, suppose it is A. And the second one is compounds containing carbon sp2x, that means halogen is attached to sp2 hybridized carbon. So this is B. Under the A, now look at these possibilities. sp3 carbon. Now it is simple. The first one is very simple, which is simple alkyl halide or haloalkane. That is haloalkane. This is the name of this chapter. Fine, haloalkane. Here only sp3 hybridized carbon are present, but some other possibilities. See, chloro is attached to CH2, and then there is CC double bond. It is true that there is unsaturation, that is CC double bond is present. But remember, the carbon with which chlorine is attached, that carbon is sp3. This is sp3. But these two carbon are sp2. Okay. But see, this category is CsP3X. So just you have to focus on this carbon with which it is attached. Rest of the part, that is not our concern. And why the name is allylic halide? It is a general term, allylic halide, but as we have only chlorine atom, so it will be allyl. Now allyl is a name of this group, which is CC double bond then CH2. So this is allyl group. You can also write it in this way: H2C double bond CH CH2. So this is the group which is known as allyl group. So if it is attached with any halogen, it will be called allyl halide. Then benzylic halides. Now what is benzyl group? Benzyl group is, we know that when it is phenyl ring, that is if you have benzene ring and there is one of the hydrogen you are replacing with Br. So this is phenyl group. But suppose if between the phenyl ring and Br, if there is some carbon present, that is CH2, then Br. So it will be now PHCH2Br. Now this group, that is PHCH2, that is actually known as benzyl. So this position, that is this carbon, is called benzylic carbon. Try to understand the difference. If it is directly attached with phenyl ring, it will be called haloarene. It is aromatic halide. But if in between the halo and phenyl ring, now you have CH2, and this carbon is sp3 hybridized, because we are discussing this under this heading CsP3X. So it is sp3 hybridized. Fine. So, and this group is benzyl group. So as it is attached with the halogen, so the name is benzyl halide or benzyl bromide, because in this case it is bromine halogen that we have taken. Okay. So this classification, is it clear? That is under CsP3 halogen bond, we have three possibilities. It may be alkyl halide, which is the simplest one, based on which you can see the name of this chapter. But there are some other possibilities when it is true that chlorine, that is halogen, is attached to sp3 hybridized carbon, but rest of the part there is some difference. Fine. Any doubt? And then we have in B category compounds containing sp2x. So vinylic halide. Vinyl group is CC double bond, and then halogen is attached. Try to understand difference with allyl. When it is allyl, then CC double bond, then CH2, then X. So it is a CsP3X, but now it is directly attached to it sp2 hybridized carbon. So that is why it is, the name is different. The group is CC double bond, this group is vinyl group. So the name will be vinylic halide generally. And if it is iodine, in this case, in this example, so that is why the name vinyl iodide. And the second possibility under this category, CsP2X. Second possibility is if directly with the benzene ring there is some halogen attached. So here the example that we have Cl, which is attached to C6H5, that is pH3, and the name will be either you can say benzene chloride. Normally, if you follow this general term, that is aryl halide, first you write aryl, that is phenyl, and then chloride. Okay, phenyl chloride. But this is also another way we can express the name, chlorobenzene. Fine. But in both cases, the common point is the halogen is attached to sp2 hybridized carbon. Fine. Any doubt? Here, one thing also we have to notice. Just come to this one, that is when we have discussed dihaloalkane, that is halogen is attached to sp3 hybridized carbon. That is dihaloalkane, it can be two types. The first type is when both the halogen are attached to same carbon, and this is known as geminal dihalide. But if they are attached to two different carbons, see now two different carbons are containing these two halogens, and this is known as vicinal. And why it is important to know, because suppose some compounds are given and it will be asked that among these compounds which are geminal, which are vicinal, because both are dihalo, but there is difference. In first case both are attached to same carbon, in the second case they are not attached to same carbon but adjacent carbon. Fine. So this is the difference between geminal and vicinal. Any doubt in this slide? Now this other classification, that is based on hybridization, we will elaborate it a little more. Based on hybridization of carbon attached to the halogen. Now when it is monohalo compounds, they can be classified into classes and subclasses on the basis of hybridization of the carbon atom to which the halogen atom is attached. And here we have two categories. Remember in the last slide we have seen two categories. The first type, which is A, where you have the compounds with sp3 carbon halogen bond. Fine. Now under this category A, the first possibility is alkyl halide or haloalkane, which you can see this name is already present in the chapter's name. In this case, the halogen atom is attached to an alkyl group, and look at this formula, CnH2n plus 1x. So when it is simple alkane, the formula, general formula is CnH2n plus 2. But now as you have replaced one H with X, so the general formula will be changed. Now see, H is 2n plus 2, but now it is 2n plus 1 because one H is less. So simply take the example of C2H6. It is ethane. So here n value is 2 and 2n plus 2 will be 2 into n, 2 into 2, 4 plus 2, that means 6. But when you have replaced one H with halogen, now it will be C2H5X. Now look at the formula. N value is still 2, but H is 5 because it is 2n plus 1. 2 into 2 plus 1, 4 plus 1, 5. Okay. So in this way, there is a change in the general formula. Now further subdivision is possible here. They are further classified into mainly three types on the basis of carbon atom to which carbon bearing halogen atom is bonded. Look at this sentence, what it is saying. Further classified into mainly three types: primary, secondary, tertiary. On the basis of what? On the basis of carbon atom to which carbon bearing halogen atom is bonded. Fine. Now when you will see the example it will be clear. But primary, that is also we also say it as 1 degree, secondary is 2 degree, and tertiary 3 degree. So in the first box, the examples that you are seeing here, the carbon with which halogen is attached, that is in bold form. See, and you have to focus on this bold carbon, because just look at this tree structure. What is the common point you are seeing? This carbon is attached to only one carbon. One carbon, one carbon, one carbon, and it is containing 2H. That means the carbon with which halogen is attached, if this carbon is attached to only one carbon, it will be 1 degree or primary. But in the second box, now this bold carbon, it is attached to 2 more carbons. Second one is also same. So that is why these 2 examples are for secondary. And obviously the last possibility, now it is attached to this bold carbon. It is attached to 3 more carbon. 1, 2, 3. 1, 2, 3. So that is why it is 3 degree, or you can also call it tertiary. Fine. So these 3 are clear, the difference between primary, secondary, tertiary, because these 3 terms are very frequently used in organic chemistry. Here we have a problem based on this. Classify the following compounds as primary, secondary and tertiary. So 3 compounds are given, 1, 2, 3. You have to mention which one is primary, or it may be more than one is primary. That is basically we have to write the structure first, and then you can understand whether it will be under the primary category or secondary or tertiary. Come to the first one. 1-bromo-bute-2-ene. Now bute, that means 4 carbon. So simply write 4 carbon chain, the first thing that you can do. Then one position there is bromo. So this is 1, 2, 3, 4. 2 position there is in. That means double bond is present. Fine. So first we'll write all the structures, and then we'll see whether it is 1 degree, 2 degree or 3 degree. The second one, 4-bromo paint 2-ene. Paint means first write 5 carbon chain, 4 position bromo, 2 position in. 1, 2, 3, 4, 5. And the last one, propane. Propane means 3 carbon, 2 position bromine, 2 position methyl. So this is 1, 2, 3. Now the first one here, 1 carbon is attached to bromine, and 1 carbon is attached to only 1 carbon. So that means it will be 1 degree. Now the second one, the bromine is attached to this 4 carbon, but 4 carbon is attached to 2 carbon atoms. So that is why it will be 2 degree. And the last one, bromine is attached to carbon number 2, but carbon number 2 that is attached to 3 methyl group. That means 3, it is attached to 3 carbon. So it will be 3 degree. So is this question clear? Why the first one is 1 degree, the second one is 2 degree, the third one is 3 degree. Any doubt? Should I repeat? So the first point is complete. That is under A. Look at the left hand side heading, compounds with sp3 CX bond. This is A. Under A, first we have seen number 1 possibility, alkyl halide or haloalkane. Here we do not have any double bond or triple bond. Fine. That is sp2 carbon is not present. Though you may think that why I am talking about sp2, because it is all about sp3. But sp3 carbon is that carbon with which halogen is attached. But that doesn't mean that in rest of the part of the molecule you will not have sp2. It may be or it may not be. So when it is not present in rest of the part, then this is the first type. alkyl halide, but it may be present in the other part of the molecule. So now we will focus on that. Now the second one is allylic halide. Remember the allylic group, CC double bond then CH2. So this group is allylic group, and this particular position, this is known as allylic position. These are the compounds in which halogen atom is bonded to an sp3 hybridized carbon atom. That is true because this carbon, that is the allylic position carbon, this is sp3. But that does not mean the other carbon has to be sp3. It may not be so. So here the other two carbon, they are actually sp2. And this particular group, that is CC double bond and then CH2, that group is known as allyl group. So that is why based on this, the name is alkyl halide. And halogen atom bonded to an sp3 hybridized carbon atom which is adjacent to CC double bond. Okay, that means this carbon is allylic position, and you can also call it the allylic carbon. So suppose this particular compound is given, that is the molecule in the box, and if it is asked that among these three carbon, which carbon is allylic carbon, then it is this one which is the allylic carbon. This is the allylic position. Fine. Now some examples, because this is the general structure. See, CC double bond CH2, then we have bromine. So this is allyl bromide. Now we also have some cyclic type of structure where you have CC double bond, and this carbon is allylic carbon. There is another allylic carbon also in the lower position, and in both these carbon you can see there is iodine atom attached. So this is also under allylic halide category. Benzylic halide, number 3. In this case, obviously benzyl group will be there. In this case also halogen atom is attached to sp3 hybridized, because the broad category under which we are discussing 1, 2, 3, that is itself sp3 carbon halogen. So obviously halogen atom will be attached to sp3 hybridized carbon. But this sp3 hybridized carbon, that is actually next to an aromatic ring, and that is why this carbon is benzylic carbon. Fine. So this position is benzylic position, and this carbon is benzylic carbon. And see, this carbon is CH2, it is sp3 hybridized because it is not part of the double bond. So that is why it is a benzylic position. And PHCH2, this group is known as benzyl group. See, we have examples. The carbon with which F is attached, there are basically two carbon. Both these carbon are sp3, but it is next to aromatic ring. So that is why this carbon, benzylic carbon, this one is also benzylic carbon. Now the second one comparatively easier to understand. This carbon is benzylic carbon, and the last one is interesting because now just compare with this structure. It is as if it's isomer, because here also you have 2F, in this case also 2F, but now both the fluorine, they are attached to same carbon. So this is also a kind of example of gem dihalide. Just forget about the benzene ring. Focus on this carbon. It is dihalide, right? And dihalide, what type of dihalide? Where both the halogen attached to same carbon. So this is true that this is benzylic halide because this carbon is benzylic carbon. But this is also true that this is also the example of gem dihalide. So same molecule, it may be different types. Fine. So it is simultaneously benzylic compound as well as it is geminal dihalide, because same carbon is containing two halogen atoms. Here we have a question. Which is an example of benzylic halide? Two examples, two molecules, their pictures are given. The first one is PHCHCl2. PHCH2 chlorine. And the second one is PH, then CH2, another CH2, then Cl. Now this carbon is sp3. This is also sp3. In both cases it is so. But it is asked which is an example of benzylic halide. So can you tell me among these two, 1 and 2, which one is example of benzylic halide based on the previous discussion? One or two, which one is benzylic halide? The first one is benzylic halide because this carbon, that is benzylic position. But in the second molecule, this carbon is benzylic carbon, but this carbon is not attached to halogen. So we cannot call it benzylic halide. So one is correct, not the second one. Any doubt?
No, ma'am.
Now after finishing A, next it will be B, that is compounds with sp2CH bond. Now the carbon with which halogen is attached, it is itself sp2. It is not that it is sp3 and then it is attached to some sp2. No. Directly the halogen atom is attached to sp2 hybridized carbon. And under this also you will have some different types. The first one is vinylic halide. Now vinylic halide, these compounds are formed when halogen atom is attached to an sp2 hybridized carbon atom of a CC double bond. So see the first example, this is CC double bond and halogen is attached to CC double bond. This is sp2 carbon. Fine. And the second example, this is CC double bond. This carbon is attached to chlorine and this carbon is also sp2 hybridized. So both these are example of vinylic halide. Try to understand the difference with allylic. In allylic there is CC double bond, then CH2, then halogen. But now halogen is directly attached to this CC double bond. So this is the difference. Next type is aryl halide. Now aryl halide, this is directly present in the name of this chapter, which is haloarenes. So all the classification that you are seeing, only two types are mentioned in the chapter. One is haloalkane and haloarene because these two are the most common. So that is why we are focusing on that. We are elaborating on that. But you also have to understand different types, different variety, possibility. All these you have to understand because question regarding this will be there. Fine. So though the chapter is all about haloalkane and haloarene, but try to understand all the different possibilities. The second one is aryl halide. So from the formula it is clear the halogen is directly attached to the benzene ring or it may be some aromatic ring. Not necessarily it has to be benzene always. Aryl means it may be any other aromatic ring also. These compounds are formed when the halogen atom is bonded to sp2 hybridized carbon atom of an aromatic ring. So if you ending the statement here, it is same as the previous one because in the previous one also it is sp2 hybridized carbon. But now see, it is sp2 hybridized carbon atom of an aromatic ring. That is the difference with the previous one. An aryl halide can be called a phenyl halide if it is not containing any other substituent. And when the aromatic system, it is specifically the phenyl system. But suppose if it is not C6H5, it may be that it is C6H4 and also containing some OH group at any position, 2, 3 or 4. So that is why better you then write AR. So pH you can write only when it is C6H5. But if there are some other groups present, you have to now write AR, short form of aryl. Now look at these examples. Here these two examples are very unique because here chlorine is attached to aromatic ring, but they are not benzene. Right? So the first one is furan and the second one is pyridine ring. These two are actually heterocycle. Heterocycle means where except carbon also there will be some other atoms. Normally oxygen, nitrogen or sulfur like this. So they are heterocycle but they are aromatic. So that is why we are discussing it under aryl halide. Fine. So these two are examples of the second type. And see, these are comparatively simpler to understand because now we have taken the benzene. and we have all the 4 halogen atoms, and depending on the halogen atoms, the name is also different. Fluorobenzene, chlorovenzene, bromobenzene, and arterbenzene. Fine. So any doubt regarding the classification? Because under classification, first we have done, it is based on how many number of halogen atoms. After that, we have seen the classification which is based on the hybridization of the carbon with which the halogen atom is attached. So 2 types of classification we have seen, and there is some subdivision also. Fine. So related problems, we have to match the pairs. In the left hand side, column 1, we have 3 compounds, and in the right hand side, column 2, total 5 names are there. So obviously 2 names will be extra. The first one, they are not actually the names, because see here general structure is given. We don't know which halogen atoms it is actually. So it is general structure, and the name is also general. In the first case, halogen is attached to sp3 hybridized carbon. There is no doubt in that. Fine. And there is no CC double bond. That is, no sp2 carbon is present. So this will be example of alkyl halide. Simple. Alkyl halide you can use only when there is no other double bond or triple. So A is matching with 2. Now the second one, remember this group is CC double bond, then CH, it is allyl group. So it will be allyl halide. So B is matching with 3. And the last one, now halogen, it is attached to sp2 carbon. But sp2 carbon, it is attached to sp2 carbon. Under this, you have 2 possibilities. It may be vinyl or it may be aryl, but we do not have any benzene ring. Aryl ring is not present, so that is why it will be vinyl halide. Fine. So C is matching with 1. So there are 2 names extra: aryl halide, benzyl halide. These 2. Now, if I suppose, though these 2 boxes are vacant, but suppose if I write it benzyl halide, it will be PHCH2X. But this type of structure is not present, so these 2 are extra. And aryl halide. Now, aryl halide means there will be some other groups present. I am writing in general G. And when we write the bonds in this way, that means the position of G, it may be ortho with respect to X, it may be para with respect to X, or meta with respect. So all these possibilities are there. So that is why I have written it in general like this: X, G. But these 2 are not present. So here A is matching with 2, B3, C1. Next question, the position of Br in the compound is given, can be classified as allyl, aryl, vinyl, or secondary. So first, obviously, we have to draw the structure. CH3, CH double bond, then C, and here we have CH3. Now after this CC double bond, there is carbon next, with which the bromine is attached. Now this carbon, it is also containing 2 more methyl group. So it is asking, so now we have drawn the structure, whether it is allyl, aryl, vinyl, or secondary. So bromine is attached to this carbon. Okay. Now if it is allyl, then remember allyl group is CC double bond, then CHC. But that doesn't mean it will not have any other substituent. So here also we have this fragment C, CC double bond, then C. It is true that there are other substituents. It is not simple CH2, CH, and then CH. There are several, but allyl group is there. But what about the second one, aryl? Aryl obviously not true because we do not have any benzene ring. Vinyl also not correct. Why it is not correct? Because when it is vinyl, the bromine, it will be directly attached to sp2 hybridized, but that is not in our case. So this is also not correct. And the last option is secondary. Now bromine is attached to this carbon, and this carbon that is attached to 3 more carbon. So it is 3 degree. So actually it is allylic and it is also 3 degree. But in option you have only allylic and it is single choice answer. So that is why this will be the correct option. Rest of the 3 are not same. But suppose it can be framed in a different way. Suppose one of the option is 3 degree, and if it is multiple choice question, then both of them will be correct because it is allylic from the point of view of whether it is allylic group. This is allylic group. CC double bond, then C. It is present or not. So it is present, so that is why it is allylic. And why it is 3 degree? Because the carbon with which bromine is attached, that is attached to 3 more carbon. 1, 2, 3. Okay. Option 1 correct. Multiple correct choice. Haloalkanes contain halogen atom attached to sp2 hybridized carbon atom of an alkyl group. So that we know. But you have to identify haloalkane from the following compounds, and it may be that more than one is under haloalkane. More than one may be correct. So we will draw all the structures. The first one, 2-bromopentane. So pentane means it will be 5 carbon. 2 position bromine. Fine. Let me draw first all the structures. Vinyl chloride or chloroethene. So ethene is CC double bond, ethylene, remember? And there is one chloro. And you can also it can also be called vinyl chloride. So it is CC double bond, then Cl. Then the third one, 2-chloroacetophenol. The third one, 2-chloroacetophenol. But what is acetophenol? Acetophenol is basically this moiety. pH ring when it is attached to COCH3, that is known as acetophenol. The name of this molecule is acetophenol. So this is a derivative of acetophenol. And what is the position of chloro? It is 2. So if this is that is with respect to COCH3 group, this is the 2 position. So this is the structure of 2-chloroacetophenol. And the last one, 4, trichloromethane. Methane is CH4. But trichloro, that means out of these 4 hydrogen, 3 hydrogen atoms are replaced by 3 chlorine. So that is why now it is this type of structure. So it is methane derivative, but tri-substituted. Now you have to understand, identify haloalkane from the following compound. And what is haloalkane? That is also mentioned here clearly. They contain halogen atom attached to sp3 hybridized carbon atom. Look at the first one. This is the carbon with which bromine is attached, and this is sp3. So this will be alkyl halide example. Second one, this carbon is sp2, so this cannot be correct. Then the third one, here chlorine is attached to this one, and this is sp2, so this is also not correct. And the last one, this carbon with which 3 chlorine attached, but this is also sp3, so this is also alkyl halide. So here correct option is not only 1 but also 4, but not 2 and 3. Is it clear why the first and last option, these two are correct? Any doubt? Next one. Which of the following compounds are gem dihalide? Remember, gem dihalide means obviously dihalide, so 2 halogen will be there. But both the halogen are attached to same carbon, and there may be some other substituents. So this type of fragment, if it is present, that will be the correct answer. The first one is ethylidene chloride, and the second one is ethylene dichloride. See the difference you have to understand. If you are in a hurry and reading it very quick, it seems as if same, but it is not same. Look at the spelling, it is different. Okay, so ethylene dichloride is basically, it is simple. Simply take ethylene, CC double bond, and 2 halogen atoms are on the 2 adjacent carbon. But when it is ethylidene, now it is actually same carbon containing 2 halogen. So these are the structures. Ethylidene chloride. Ethylidene means what? Eth, it means always 2 carbon. So it is 2 carbon. The second one is also 2 carbon. But it is ethylene dichloride. That means ethylene what? Ethylene is CC double bond, CH2 double bond, CH2. But as if you remove this double bond, and in place of that you are now having 2 chlorine. So that is why the name is generated from the structure ethylene. So that is why the name is ethylene dichloride. But ethylidene chloride is something different. Ethylidene chloride is, first you have to draw this 2 carbon chain, and then single carbon is containing 2 different halogen. Fine. So this the first one, obviously it is J, but not this one. So this is correct answer, but not second one. Now come to third and fourth. Methylene chloride. What is methylene chloride? Meth, it means what? Single carbon. And methylene group, it is, suppose someone is asking what is methylene group, what you will say? You will say H2C, that is CH2. But carbon must have 4 bonds, so rest of the bonds there will be halogen. It is true that it is chloride here, so it is CH2Cl2. So this is also JM dihalide, right? This is also correct option. Benzyl chloride. Now this is obviously not JM halide, because benzyl chloride there is only 1 chlorine. So how it can be JM dihalide? Fine. But suppose if the structure is like this, another chlorine is attached, then it is at benzylic carbon. That is the 2 chlorine, they are attached to benzylic carbon as well as their chain. But that is not the structure of benzyl chloride. So that is why this is the structure, right? But this is not the correct choice. So here correct option 1, 2, 3, 4. Only 2 are correct, 1 and 3. These 2 are examples of JM dihalide. Okay. So after finishing classification, there is nomenclature. Now there will be some specific rules based on which you can do the naming. Though you have already seen there is some common names we are using. So that is also one type of naming. But when it is IUPAC, there are some specific rules that you have to know. Otherwise, you will not be able to write the structure. Naming of the compounds by following a certain set of rules, that is known as nomenclature. Now see a new term you can find here, which is trivial names. Now trivial names are not common names. There are 3 terminologies we are using. One is IUPAC nomenclature, where you will follow some definite rules. Another thing is common name. Now these 2 we have already seen. Common names means they are not based on some specific rules, or yes, it is true sometimes there are rules, but it is not so strict rules like IUPAC. But common name, why it is we call it so? Because we use it very frequently. That is the second type. And what about trivial? Trivial names are basically based on the name of discoverer or the nature of the compounds, or sometimes the place of discovery. So you can also find some trivial names but in some cases, not always. The system of trivial names was not standard, leading to the need for a standard system for the naming. So they are not standard because it is based on the name of discoverer or the place where it is discovered. So obviously they are not standard, and standard system must be used so that we can use the names universally. Okay, so suppose you are here, you are saying one name, and someone's at other corner of world, he or she is using some other name, so there will be some confusion. So there must be same name for a particular compound. If it is not having same name, there will be confusion. So that is why some standard system, which is mostly the IUPAC nomenclature, that is required. This is the importance. But trivial names, common names, these will also be always there. So common name, it is different from a trivial name in the sense that it also follows a rule for its nomenclature, though the rules are not so strict that you can find for IUPAC, but still it has some rule. But trivial names, compared to trivial names, it is completely different. Fine, because trivial names are based on name of discovery or the place of discovery. And IUPAC name, the full form is International Union of Pure and Applied Chemistry. IUPAC naming system, it is actually the standard system where we actually follow some rules, and it is the generally used by chemists. Okay. So here, if you look at these two examples, and what is trivial names, that is already mentioned in the second point. So we are not going into the details, but here see, we have both same compound. Suppose the general structure is Rx, so R is alkyl group, X is halogen. Now, if it is IUPAC name, we say haloalkane. But when it is common name, now see, alkyl halide. So when it is IUPAC, you are saying halo first, then you are saying alkane. But when it is common name, you are first saying the alkyl part, that is the carbon hydrogen part, then you are using the halide. So there is obviously difference. Now Rx, suppose if Rx is CH3CH2Br, so this is the R, this is X. Now try to follow the IUPAC name halo then alkane. That means bromo, which is halo, alkane is ethane because it is containing two carbon, and common name will be alkyl first. That means it is ethyl group. The alkyl group is ethyl, and then halide. That means it is bromide. So in this way you can compare, and also you can understand the difference between these two types of naming, common name and uncommon. Okay. So regarding all the slides, if there is any doubt, please mention, because we are at the end of this session. So if there is no doubt, we are ending the session here. Thank you for listening.